right? So we are a little bit more than halfway through the unit now, which is why, as some of you noticed, I set the exam date. All right, it will be November the 8th. We will likely already be done the unit for a few days by that point, but that's the date I've set it for. That way you get more than 2 weeks notice of when the exam will be, and that gives you lots of time to study and come in and see me for help. So you may want to enter that date into your phone, right, so that you remember it for studying purposes. Tomorrow, we will be working on your Newton assignment. Okay, so it'll be like the vector assignment. It'll be, 10 or 12 problems to do with Newton's second law, okay, that you have to solve and hand in 4 marks. Okay, that'll be going on tomorrow. And I think I'm going to not have a quiz tomorrow, and then we'll have the entire class to work on just that assignment, and hopefully a lot of you will get it done in class and you won't have any homework on it, because you have a few things obviously coming up. Your Newton lab is due tomorrow, so make sure you have that done. Okay, your friction lab is due next week, so make sure you're working on that and getting it finished, and obviously you have a unit exam coming up. Okay. All right, work-energy theorem. Here's the good news about work-energy theorem. It hasn't changed since you learned about it last year. Okay, in fact, it's exactly the same as it was last year. The only thing that we will do differently in Physics 20 than from Science 10 is that we will deal with problems where both potential and kinetic energy change, whereas in Science 10, you only dealt with problems where when work was done, potential changed, or when work was done, kinetic changed. You never had to deal with both. In the end, it isn't any harder. I don't know why we don't do it in Science 10. Okay, you just have to keep track of 2 types of energy. Not a big deal. All right, so we need to know what work is. What is work? When you do work, what do you change? Well, the force exerted could change, but for most of our purposes, it's a constant force. Okay, distance could change for sure. Okay, but if I do work on something, what am I giving it? Energy. Okay, if I do work, I am changing the energy of something, which is why we often write work as a change in mechanical energy. All right, now, quick review. Mechanical energy is the sum of an object or system's kinetic and potential energy. So when I do work, I could change both types of energy, kinetic and potential. Okay, we need to understand the relationship between force and work, and that's the formula that you learned last year. Work is force times distance. Right? In Science 10, you learned it just that way because you only did one-dimensional problems. What we're going to add into that is that sometimes force can be vectored in a different direction than the work. Okay, all it does is add in cos of theta times d. So we take, if we had an angled force, okay, like this, but the box is moving horizontally along the surface, work isn't being done in this direction, it's only being done in this direction. So we would need the horizontal component of that force. That's why we use F cos of theta times d. It would give us the amount of that force that's actually doing work. Okay. Last thing, learn that depending on the situation, work and energy can be equal, right? If I do work on something that initially had no energy, then all the work I do will become its mechanical energy. So if it had 0 joules of energy and I do 100 joules worth of work on it, it will now have 100 joules worth of mechanical energy, be it kinetic, potential, or both. Okay, that ringing a bell a little bit from last year. Okay, work is a change in energy, okay, a change in mechanical energy, which means final mechanical energy minus initial mechanical energy. That's always what delta means. Okay, delta means change, so it always means final minus initial. All right, do we remember from Science 10 how we calculate mechanical energy? because I told you just a minute ago what it was. Exactly. And mechanical energy is the sum of an object's potential and kinetic energy. Now in Science 10, we only learned about one type of potential energy, and that was gravitational potential energy. And for the purpose of this unit, that's really about all we'll use as well. But when we get into the last unit of this course and we talk about elastic potential energy, okay, we'll work that in as well. It doesn't really change anything. Energy is energy. It's just how you get it. Okay, gravitational potential energy you get by moving away from the Earth's surface. Okay, elastic potential energy you get by exerting a force on an elastic object that could rebound to its original shape, so a spring or a rubber band or something like that. Okay, alrighty. So, strictly speaking, work happens if a force is exerted over a distance. Okay, both of those things have to happen in order for work to be done. Okay, if I just stand here and push on the wall, okay, am I doing any work? I get tired, but I'm not doing any work, okay? I'm not changing the energy of the wall. No matter how hard I push on it, I am not going to change either the kinetic or potential energy of the wall, and as a result, I am going to accomplish nothing, okay? I will do no work on the wall. Weird thing though, I don't do any work on the wall. I don't transfer any energy to the wall. Why do I get tired? Well, not so much friction, but when I push on the wall, what does the wall do? Right. Okay, the wall pushes back on me, which then means that my muscles get shorter. Okay, they contract. When I use them, they get shorter. So there's a force being exerted on me over a distance that shortens my muscles. I'm actually having to absorb, okay, the work that the force that the wall is doing or exerting back on me. Okay, so the wall exerts that force back on me. I have to brace myself against that force to stop from moving. That's what tires me out. It's not that I'm transferring energy to the wall. Okay, I'm bracing myself against the Newton's third law reactive force coming back from the wall. Okay, so even though I don't transfer any energy to the wall, I'm still going to get tired. Okay. All right. So in this case here, I have a person who's pushing a stalled car. Okay, when they push the stalled car, its velocity changes. Okay, because it was stopped and then it's moving. Okay, even if I just push it at a constant velocity, am I still doing work? Yeah, not on the car, but against not against gravity, it's the level surface, against friction. Okay, so I do work on the car when I accelerate the car from rest to whatever speed I can get it rolling at. Once it stops accelerating, that is, I can't push it any faster, I still have to do work. But now I'm not changing the energy of the car. I'm doing work against the forces working against the car. Okay, and so that energy ends up in the surroundings as heat and sound and other things like that. Okay, so I'm still doing work, but I'm not doing work on the car. I'm now essentially doing work on the surroundings by changing their energy instead. Okay, everybody all right with that idea? Okay, the only way I'm doing work on the car is if I'm changing the energy of the car. Okay. All right, so the diagram shows that this constant force points in the same direction as the displacement. Okay, if I'm doing work, if I'm pushing to the right, okay, and the car moves to the right, okay, then I'm doing work, okay, in that way. Now, weird thing is that work, just like energy, is actually a scalar quantity. Right? The only reason I have to worry about direction in the formula is I have to make sure that I'm only using the part of the force that's going in the direction the object moves. Okay? It's not that work is a vector quantity, it's that the force and the displacement are, okay? And that they have to be in the same direction. All right, so that's where this formula here, okay, comes from. All right, and remember that work does not convey directional information and is thus a scalar quantity. All right, questions on that? Okay, so work is scalar because what it changes, the energy, is also scalar. Right? So it doesn't matter whether I push the car east or north or south or whatever. Okay? If I change its velocity from 0 to, let's say, 3 meters per second, okay, it won't matter which direction it's going. It will have that much energy and the same ability to do work no matter which way it's going. Okay? I wouldn't want to, stand in front of it. Okay, so the units for work, remember the formula for work is force times distance. So that means newtons times meters. So the units for work are a Newton meter, otherwise known as a joule. All right, so a Newton meter is a joule. Okay, in other words, it is a kilogram meter squared per second squared. That's the fundamental units for a joule. All right, because the fundamental units for a Newton are kilogram meters per second squared, mass times acceleration. Okay, well, I have kilogram meters squared, or kilogram meters per second squared multiplied by meters. Okay, I just end up with meters squared on that as well. Okay, but thankfully we get to just abbreviate that as joule. All right, so these girls are pushing on this rock. The rock obviously doesn't go anywhere. Okay, are they doing any work? Yes. On the rock? No. Okay, they're not doing any work on the rock. The rock isn't going anywhere. I'm not changing the energy of the rock. Okay, but same as the example of me pushing against the board, okay, I might be doing work on the surroundings. I may be losing energy to the surroundings. Okay, that would be mostly thermal energy, okay, but it's still energy being lost. But what I'm not doing, or what they're not doing, is any work on the rock. Okay, because there's no change in energy of the rock, there's no work being done on the rock. Okay. All right. Oftentimes you get a force and a displacement that are not in the same direction. Okay. Case in point, if you are at the airport and you're rolling your luggage along the floor. All right. Most luggage now has 2 wheels on the bottom, and you pull it at an angle. Right. When you're pulling at an angle, you're not pulling it straight forward. You're pulling it forwards and up. Are you lifting it off the ground? Okay? Your luggage doesn't leave the ground, it's rolling on the ground, which means you're not changing its potential energy. You're not changing any energy vertically, right? But you are changing its energy horizontally. That would be you're accelerating it from 0 to whatever speed you get to, right? So we could figure out that by using not this force, not the pulling force, but the component of it that is in the direction the object is going, in this case, the suitcase. The suitcase is moving horizontally, so only the horizontal component of my force is doing work. All right, not the full force, just the part of it moving or pointing in the same direction as the movement. Does everyone follow me there? Okay, the work has always got to be done in the direction of movement. Okay, that means I can only use the force directed in that direction as well. All right, so that means we calculate that. Okay, it's the adjacent side to that triangle. So I would go this force here, okay, times the cos of theta, and that will give me the force, the part of the force that's actually doing work. The vertical part of that force is not doing any work because the suitcase is not moving vertically. All right, everybody okay with that? Right? If it's not moving vertically, then there's no change in potential energy. Right? M times G times H is how we calculate potential energy. Right? Because there's no change in height, there's no potential energy being changed. So we're only doing work horizontally. Okay? Now, if I pull this thing horizontally at a constant velocity, am I doing any work on it? I only do work if I make the object accelerate, okay? Because that means that there's actually a change in kinetic energy, okay? Remember the kinetic energy, or change in kinetic energy would be 1/2 mvf squared minus 1/2 mvi squared. This is the formula for potential energy, right? If there's no change in velocity, then there's no change in energy, and thus there's no work done on the object. But it still takes energy to pull it along even at a constant velocity because I'm working against friction. Okay, you can hear the luggage carrier. Okay, it's making noise, heat's generated. Okay, all of that kind of stuff. That's where your energy is going, right? But it's easier to pull it once it's moving than it is to get it moving. You have to exert more force to get it moving because you're actually changing the energy of the object. Okay. All right. Everybody all right with that idea? Okay, so it's this idea that is where it is the place where we can apply ideas to increase efficiency. Okay, anybody drive a hybrid car? That's kind of what I thought, but that's all right. I don't either. Okay, the idea behind hybrid cars is that to travel at a constant velocity requires a lot less force and a lot less work than to accelerate something. Okay, so a hybrid car works on this principle. Put a smaller engine, a smaller internal combustion engine in a car, and have an electric engine there to assist it when there's high energy demand. High energy demand comes when you are accelerating. Okay, so in a hybrid car, when you are accelerating away from a stoplight, the internal combustion engine is running, and the electric motor kicks in to assist it. Okay, when you are traveling at a constant velocity, like cruise control on the highway, the electric engine is not working. Only the internal combustion engine is working. But because it's smaller, it doesn't use as much fuel as a larger motor would. Okay, if I'm just driving a normal car, okay, like my truck, right, on the highway in stop and go traffic, I only have one engine, and it uses more fuel when I'm accelerating. Okay, but if I had a smaller engine with an electric motor to assist it, it wouldn't use as much energy when it's accelerating because the electric motor would kick in to help. All right, everyone kind of follow me on that. Okay, so the idea to increase efficiency is there for a hybrid car. You're going to use the same amount of energy, period, to accelerate the car, but electric motors are more efficient than internal combustion motors are. Okay, so that would result in you using less fuel during acceleration and way less fuel while you're traveling at a constant velocity because you now have a smaller engine to feed. Right? Some vehicles, I think mostly Chevy does this, okay? But some vehicles, when you're on the highway and you're not accelerating, it will kill off half the cylinders. Okay, so if you have a V8, okay, it has 8 cylinders that are going up and down. While you're on the highway, you don't need all 8 cylinders firing because it doesn't take a lot of energy to keep you moving at a constant velocity. So it'll shut half of them off. It'll essentially run as a 4-cylinder engine until you step on the gas to pass somebody, then it'll kick the other 4 back on and give you the power you need to do that. Okay? It's a good way to increase efficiency. You don't need to be firing on all cylinders when you are traveling at a low energy requiring condition. Okay? So these are all applications of work-energy theorem. Okay? It takes lots of energy to change velocity, not as much to keep it going at the same. All right, questions on that part there? Okay, let's try this one. Okay, simple example, and the answer is right there underneath it. But okay, we want to find the work done by a 45 Newton force pulling this luggage carrier at a 50-degree angle for a distance of 75 meters. All right, so we're trying to find the work done. Okay, we know that work is force times distance. In fact, it's force times the cosine theta times distance because our force is directed this way, but the luggage carrier is moving this way. Right? So I don't need all of this force. Okay, I only need the horizontal component of it because that's the only part of it that's actually doing work. So that's where the F cosine theta times D comes in. I take my 45 newtons worth of force, that's the force in the handle, multiply it by the cos of 50 to get just the horizontal part of that, and then multiply it by how far it's pulled. All right. In the end, that means I'm going to use 2.17 times 10 to the 3 joules worth of energy to pull this luggage carrier. Right? And that would just be pulling it at a constant velocity. I'm not changing its energy at all. That's how much energy I would lose to the surroundings because of friction. Okay, 2.17 times 10 to the 3 joules worth of energy. So it's kind of a good workout to carry luggage around or drag luggage around. Okay, yeah, well, at least one arm anyway. Your luggage pulling arm would get jacked maybe. Okay? Something like that. All right, And to do this, I didn't even need to know the mass of the luggage carrier. Okay? This is just how much work would be done exerting that force over that distance. Okay? Wouldn't matter what I was doing. If I was exerting that force over that distance, that's how much energy I would expend. Okay? All right. This is a weird one. I just finished telling you a few minutes ago that work and energy are scalar. And now I have a problem up here that says positive and negative work. Do those two ideas contradict each other? They seem to. But here's the thing. What we mean by positive and negative work has nothing to do with direction. It has to do with whether you're giving the energy or taking the energy. Okay? From my perspective, okay, if I am pushing the barbell up, I am changing the energy of the barbell because on my chest, it has no potential energy. All right? It can't fall any further. Once I push it up in the air, it now has potential energy because now it could fall. All right? So I have done work. I have transferred energy to the barbell. From my point of view, that's negative work because I've lost energy to the barbell. From the barbell's point of view, that's positive work. It has gained that much energy. Everybody follow me there? Okay. When I lower the barbell, okay, do I still have to exert a force? Yes, if I don't want to have a flat rib cage, I want to exert a force upwards on the barbell. If I drop it, I'll die. Okay? Because I'm huge and that would be a massive amount of weight. Okay? It would crush my chest. Okay, so what I want to do if I'm doing this properly is I want to lower the barbell slowly. Okay, and I've seen like high school kids in the gym, okay, and they're all about the upward part of the movement and so not about the lowering part. Okay, you're missing half the workout if you're that person who does bench press like this. And you just drop it back down. Okay, you're not getting the other half of the workout. Okay, you want to lower it slowly because when you lower it, that requires just as much force as it does to raise it. Okay, if you're moving it at a constant velocity in both directions, you have to push just as hard up as you do to lower it. Okay, so you're working your muscles in both directions if you do it properly. Okay, you ever watch like people who take weightlifting very, very seriously, and you watch, they will go up slowly and down slowly. Okay, they know they maximize their gains by doing that. Okay, if they lower it quickly, they're not getting anything out of it. All right. So when I push the barbell up, then we're going to say the barbell weighs 710 newtons. That means if I want to lift it at a constant velocity, I have to exert how much force? 710 newtons, right? The net force would be 0 then. All right, so I'm going to exert 710 newtons upwards, and I'm going to move it 0.65 meters. All right, so I'm going to say that, okay, this direction here is like 0 degrees, straight up. Okay, straight up 0 degrees. When I lower it though, okay, it's now going to move 0.65 meters at what angle? 180. Okay, punch into your calculator the sine of 180. Nope. Are you in degree mode? Sorry, not sine, cos of 180. Sorry, cos of 180. -1. Sorry, I said sine, I meant cos. Okay, so when I push the barbell up, okay, I'm going to go force times the cos of 0, okay, times 0.65, right? So I'll have my 710 newtons times the cos of 0 degrees, which is +1, by the way. If you punch that in, it'll be +1, okay, times the distance, 0.65. When I lower it, I'm exerting 710 newtons times the cos of 180 degrees, the reverse direction, times 0.65. Okay, well, in both cases, I get the same number. It's 460 joules to lift it. It's -460 joules when I lower it, because from the barbell point of view, when I've lowered it, it has lost its energy. Okay, so its change in energy when I lower it is negative. Is it doing work on me when I lower it? Yeah, it is. Okay, I have to exert that force to lower it back down. I have to absorb it. It would probably say from the barbell's perspective or on the barbell. Okay, something like that. It would imply it's here. Okay, if it says how much work have you done, then you would say I have done negative 460 joules worth of work because I lost it to the barbell or I gave it to the barbell. Okay, that's a good question. All right, so like we said, the work lowering is negative because essentially the energy is now being lost from the barbell on the way back down. Okay, so we're not saying that work is vector, it's not, but work can be I gave it or I received the energy. Okay, and that's where the positive and negative comes in. Okay, so the other thing we have to remember is that in order to do work, you have to have energy. Okay, this is the, well, as some people would say, the chicken and egg argument for the work-energy theorem. All right, work is a change in energy, but if I'm going to do work, I have to have energy to do that. All right, I can't do work on something if I don't have energy to give. All right, so when your parents wake you up and say, "Hey, go shovel the driveway or go mow the lawn," like, I don't have any energy. Well, you're lying, you do, or you'd be dead. Okay, and secondly, you just don't want to. Right, but if you literally had no energy, you would fully be incapable of shoveling the driveway or mowing the lawn because that's work, and you wouldn't have any energy to do it with. Okay, so you have to have energy in order to do work. All right, now I say the whole like chicken and the egg thing, but everybody knows which came first. The egg. Chickens are birds. Birds evolved from reptiles. Reptiles lay eggs. Hence, the egg came before the chicken. So the next time somebody goes, well, what came first, the chicken or the egg? You can unequivocally give them the right answer. Okay, the egg came first. Okay, I don't do that. Yeah. All right. So work-energy theorem states exactly this, guys. Okay. Work-energy theorem says that work is a change in mechanical energy. And what we mean by that is this, okay? That when work is done, okay, we are going to take the final mechanical energy and we are going to subtract the initial mechanical energy, which for a physics 20 problem means this. Work is equal to, okay, the final potential plus the final kinetic minus the initial potential plus the initial kinetic. Okay, because we said mechanical energy is kinetic plus potential. Right? Everybody all right with that? So I can expand this out further, and it might actually look a little bit familiar to you from Science 10. Okay, that is that work is m times g times h final plus 1/2 mvf squared minus m times g times h initial plus 1/2 mv initial squared. Okay, does this look like the conservation of energy roller coaster questions you did a little bit last year? Okay, where you had all those different energies in it. Okay, only thing that's different from those roller coaster questions is that in the roller coaster questions, this bracket and this bracket were equal. There was no work done because there was no change in energy. It was conserved from the top of the roller coaster to the bottom of the roller coaster. Now we're looking at situations where energy is not conserved. Work is being done. Okay, there's going to be a difference between the top and the bottom, okay, or something like that. The final and the initial will not be the same. Right? This would be more like a real world situation. Okay, on a roller coaster, is energy truly conserved? No. Okay, if it was, the second hill could be just as high as the first hill because no energy would be lost. Okay, but roller coasters are not 100% efficient. That's why they're so noisy. It's not because there's people screaming their guts out on them. It's because they're also physically quite noisy. Okay, the wheels, the track, all of that, there's lots of friction there. Okay, the things are really, really loud. All of that represents energy being lost. Right, so the difference in energy between the top hill and the bottom hill, okay, the first hill and the last hill, okay, is the amount of work being done against non-conserved forces like friction, okay, throughout the ride. All right, so make sure, guys, that you have something about this written down, okay, because this is the work-energy theorem that we're going to be working on from here on out. It's very, very similar to what you did last year, except last year you would have never had both kinetic and potential in the same question. Now you will. Okay, so there's going to be a fair amount of manipulating here, but none of it is like really difficult. There's just lots of things to move, right? If a question asked me, here's how much work is done, and gave me some information about the final, it might ask me, find out what the initial height of the object was. So I'd have to solve for HI. That would be isolate HI from everything else. Okay. So again, not terribly difficult, but it's going to be a lot of moving stuff around. Okay, questions on that? Okay, really we're not saying anything different than we said last year in Science 10. We've just added in now that we're dealing with both kinds of energy as opposed to just one. All right, so we're going to go over a couple of examples here, not that one. Okay, we'll try number 1 together here first. Okay, so I've got this sled, okay, and I'm pulling it horizontally, okay, or along a horizontal surface, but I'm pulling it at an angle of 42 degrees above the horizontal. How much work is done to pull the sled 160 meters? Okay, so they're asking me how much work do I do pulling this sled? I'm not accelerating the sled. They never said anything about that, okay? I may just be pulling it at a constant velocity and working against friction and other things, okay? But what I have is a 620 Newton force directed 42 degrees above the horizontal, okay? They don't tell me the mass of the sled. It doesn't matter. All I know is that I'm going to pull that sled 620 meters horizontally. So this 620 newtons is not directed horizontally. So I'm not using all of this to do work. I'm only using the horizontal component of it, okay? The part of it that is directed in the same direction the object moves. So this is where that whole work equals F cos of theta times D comes in. I know the force, I know the angle, and I know how far it's being pulled. Okay, so I can just plug in my numbers here and go 620 times the cos of 42 degrees. That'll get me the horizontal component, okay? And then I multiply that by how far it's being pulled, 620 meters. No, sorry, 160 meters, sorry. 160 meters. Okay, so when I plug all that into my calculator, so I have 620 20 times the cos of 42 degrees. Okay, times 160. All right, so I do 73,719 joules worth of work. That's a lot. Okay. All right, I want you guys to try number 2 and number 4. Okay, we won't worry about number 3. It's not that you guys couldn't do it, but we'll save a little time and try just 2 and 4 for right now. There's actually, I want to say 2 different ways, but they're actually the same mathematically. 2 different ways to do question number 4. All right. Most of us, because we're doing this F cos of theta times D thing, are probably looking at saying, all right, well, I can calculate the force of gravity because that's what they tell me to do. How much work does the force of gravity do? The force of gravity would act over 20 meters, right? So people are saying, all right, work is force times distance. I'm not going to have any angle because it's straight down. So I'm just going to say 60 times 9.81 times 20 meters. Okay, that gives me the force of gravity times distance. All right, we also said that work is a change in energy, right? Okay, gravity is changing his potential energy, agreed? He's going to have less of it after the 20 meters. So could I also do this? Could I use the potential energy formula and calculate the change in his potential energy by using the change in his height, which would be 20 meters? Yeah. You know why I can do that? Because it's the same thing that you did here. m times g times h. Okay, that's where that formula comes from. It's force times distance. But when you change something's potential energy, you're working against the force of gravity, right? So that's why it's force times distance. All right, questions on number 4? Okay. I want you to copy this one down. I'm going to walk through it with you. Okay, but this is a question in which, okay, we have a change in both potential and kinetic energy. You won't have done one like this in Science 10. Okay, so I need you to copy this one down, and then we'll walk through it together. So we just did a couple of problems where we solved for the amount of work done by using force times the cos of theta times d. Okay, and while that formula is effective in situations like that, I find that it's less effective when we start getting to kind of bigger, more involved problems. When you get to a more involved work-energy theorem problem, you need to look at this, that work is a change in mechanical energy, right? In order to accelerate this box up this ramp, right, I obviously have to do work, okay? And I have to do work because I'm changing its mechanical energy, not just its potential energy, okay? Yes, it will have more potential energy at the top of the ramp than at the bottom, but it's also going faster at the top of the ramp than it is at the bottom. I'm accelerating it up the ramp. I have to change both its potential and its kinetic energy. Right, so to figure out how much work is done, I want to go to this formula here, and I want to expand it out like we did a minute ago. That is that work equals, okay, the change, so that would be the final potential plus the final kinetic minus the initial potential plus the initial kinetic. Okay, so I'm taking final and subtracting initial, just like I do every time I see delta. Everybody all right with that so far? Okay. Now, I need to expand that out even further. I need to put in the formulas for potential and kinetic energy. So I'm going to have m times g times h final plus 1/2 mv final squared minus, okay, m times g times h initial plus 1/2 mv initial squared. Right? So all I've done is just put in the formulas for potential and kinetic energy into that. Okay? I know it looks long and complex, but right now, okay, really all it is me, I have to plug numbers in. Okay? I just have to plug numbers in at this point. Right? Do I know the mass of the box? Okay. I know the mass of the box. Okay. I know the height of the ramp, which means I know its final height, and its initial height would then be assumed to be 0, right? And I know that at the bottom of the ramp, it's moving at 1 meter per second, and at the top of the ramp, it's moving at 4 meters per second. Okay, I have all of those variables. Okay, even though that's a long equation that I have written there, I know all of those variables. I can easily now calculate the work done in moving this thing from the bottom to the top of the ramp. All right, so all I'm going to do is plug in my numbers. So I'm going to have 1.2 kilograms times g, 9.81, times the final height, which we said was 0.850. That's the maximum height of the ramp. Right? Whoops. And then I'm going to add to that 1/2 times the mass, 1.2 kilograms, times the final speed, 4 squared. Right? Then I'm going to subtract the initial stuff. Now, I could write in m times g times h initial, but h initial is what? 0. There is no potential energy at the bottom, so I'm not even going to bother writing it. There is some kinetic, however. 1/2 times 1.2 times 1 squared. Okay, it was moving at 1 meter per second when at the bottom of the ramp. Okay, so now all I have to do is punch that into my calculator. Whoop. Oh, I put a bracket on there when I didn't need to. Okay, and then I'm going to subtract from that my initial energy, so 0.5 times 1.2 times 1. Okay, I don't need to bother making it squared because 1 squared is 1. Okay, so I have 19, I'm going to do 19 joules worth of work. Oh, it's 4 squared, right? So right here, we're at 4 squared, I just wrote in 16, because that's 4 squared. All right, so I'm doing 19 joules worth of work in accelerating this box up the ramp. Right? So you would have done questions similar to that, except you would have only had, you lift an object from the floor to the top of a desk, and that's 1.2 meters. Calculate the work done, and you would have just calculated the change in potential energy. Okay? Or you would have had a question that asked how much work is done in accelerating a 3,000 kilogram truck from 0 to 5 meters per second, and you would have calculated the change in kinetic energy and been done. Okay? Now, both types of energy can change. That's the only difference between Science 10 and Physics 20, is that both kinds of energy can change at the same time for us here. Okay. All right, questions on how we did that one? All right, if I was given the work and not told the final speed, would I have been able to calculate it? Yeah, okay, so I would just then solve for VF. I'd have to move a bunch of things around, but I could do it. Okay, and that's really about the only way that these questions would change for you, is if I gave you the amount of work done and asked you to calculate one unknown variable in the equation. Okay, let's have you guys try just 1 and 2 for right now. Okay, don't worry about number 3, just 1 and 2 for right now. So as I was saying to you before, in order to solve question number 1, I need to find the change in mechanical energy, because that's the work done by the rope. Had they just jumped off, okay, they would have had full conservation of all of their initial energy. If they had just jumped off and there was nothing to slow them down, they'd crash into the ground with the same amount of mechanical energy they had at the top of the cliff. But they have a rope. The rope saves them, because as the rope goes through the braking mechanism on their belaying apparatus, okay, then it whistles and it hums and it gets hot. Okay, that's why you have to wear gloves, okay, when you're rappelling, and you really want to avoid touching, okay, the carabiner, okay, that you're using for the rope to run through, because the aluminum gets really, really hot as the rope goes through it. Okay, so we're looking here for the amount of work done by the rope and the climbing apparatus as they descend down to the ground, because obviously if they jumped off, they'd be going a lot faster than 5 meters per second when they hit the ground. So a lot of energy was removed here. So what I need to look at first is that work is the change in mechanical energy. So that means I need to have final potential plus final kinetic minus initial potential plus initial kinetic. Now, looking at the situation, are any of those energies 0? Okay, this is where I want to simplify if I can, right? At the top of the cliff, how fast were they going? 0. So they had no initial kinetic energy. Similarly, at the bottom of the cliff, they have no potential energy. All right, so now my life just got a heck of a lot easier. My work is just going to be equal to the final kinetic energy minus the initial potential energy. Okay, that's all I'm going to have to find. So I just have to go 1/2 mvf squared minus m times g times h initial. And I'll have my change in mechanical energy, or the work done by the rope. And this is going to come out positive or negative? Negative, because they've got a lot less energy at the bottom than they had at the top. Most of it was lost to sound and heat as they descended. All right, so we have 1/2 times 72 kilograms, okay, times 5 meters per second, but it's squared, okay, and then minus 72 times 9.81 times 25 meters, which was the height of the cliff. All right, so when we do that, Okay, so we're getting negative 16,758, but I think we only have, what, 2 significant figures? 3 significant figures. So we would say that that would be 1.68 times 10 to the 4 joules of work done by the rope. Okay. All right, how many people are on number, I said do number 2, right? But not number 3. How many people have done number 2? All right, I'm going to give you a little bit more time on number 2 then. Okay, let's look quickly at just part A of number 2. Okay, so number 2 says a force of 150 newtons up acts on a 9 kilogram mass, lifting it to a height of 5 meters. All right, I have force and distance. Is there an easy way for me to calculate work if I have those two things? Okay, then that's what I'm going to do. Okay, if I have force and distance, obviously I want to take the simpler way to calculate it than to try and find the changes in energy. Plus, I don't know anything about speed changes. Okay, they didn't mention if there were any, but there probably were. All right, so I'm just going to go that work equals F. I'm not even going to write the cos to theta part because it's a straight, the force is in the same direction as the displacement. All right, so I'm just going to take that 150 newtons and multiply it by 5 meters. Okay, so we're looking at 750. Is that right? Okay, 750 joules. All right, so 750 joules worth of work was done. All right, now calculating the change in potential energy here is pretty easy. So I want you to calculate that and then see what you noticed about how much potential energy changed and how much work was actually done. How many people have part B done already? Okay, well, let's just look at it then. All right, so if I want to calculate the change in potential energy, that's just going to be m times g times h final minus m times g times h initial. Since this thing started on the ground, initial energy was 0, okay? All I have to do is calculate how much gravitational potential energy it has when it's at a height of 5 meters. All right, so that's simply going to be, it was 9 kilograms, right? Yeah. All right, so 9 times 9.81 times 5. Okay, so there's the change in potential energy. Did I do more work than that? Okay, when I went force times distance, it said that the force did 750 joules worth of work, only 441 of which was responsible for changing the potential energy. What did the other energy change? The kinetic energy. Okay, this thing was not just lifted, it was accelerated upwards. So I changed not only the potential, but also the kinetic energy of the object with this 150 Newton force. Okay, can I figure out how much I changed the kinetic energy by? It's what's left. Okay, if I did 750 joules worth of work, 441 of which was potential, whatever's left is what changed the kinetic energy. All right, so all I'm going to do is go 750 minus my answer. Okay, so 308 joules of that energy changed the kinetic energy of the object. Now, that's where that question ends. I would ask this further question. How fast is the object going now? Assuming it started from rest, how fast is it going now? See if you can figure that out. I'll give you a minute. Okay? Assuming it started from rest, how fast is it going now? I will give you this little hint. It requires only one simple calculation. Okay, so here's how this works. The most important part of what I said was, assuming it started from rest, how fast is it going now? Well, what we just calculated was its current amount of kinetic energy, right? This is how much we changed its kinetic energy by. If it started with none, this is how much it has now. Is the formula for kinetic energy 1/2 mv squared? I now know 308 is my kinetic energy, and they told me the mass of the object was 9 kilograms. Can I calculate how fast it's going? Okay, all you have to do is manipulate this for v, right? Which means you'll have E over 1/2 of m square rooted will get you V, right? I just divided both sides by half of M and square rooted to eliminate the square. Okay, so that'll be 308.55 divided by 1/2 times 9. Oh, not 9, sorry, 4.5. Whoops. 308.55 divided by 4.5, half of 9.81, or 9.8, sorry. Okay. So it's moving. Oh, and then I got to square root that. Sorry, square root of that. 8.3. All right. It's moving at a speed of 8.3 meters per second now as a result of that force. All right. So nothing like terribly difficult. Okay? It's very similar to what you would have done in Science 10, except now you have both kinetic and potential energies changing as opposed to just one. Okay. All right. I think we will leave it there for now. So no quiz tomorrow, but be ready to work. If you don't want to have more homework, be ready to work tomorrow. All right, I will give you that assignment and you can get going on it and have the whole class to work on it.